In this lecture, we will continue our discussion of using deep learning for supervised learning tasks. Last time, we talked about how we can use convolutional networks to solve recognition tasks, and we have talked about a wide range of tasks here, from pixel level from image level tasks like image classification to pixel level semantic segmentation. And then we also talk about how we can use fast RCN to do instance level tasks and combine them to do instance segmentation and pose estimation. And later we also talk about how we can perform those tasks on video domain to do object tracking and even 3D object tracking. So this time we will use a lot of things we have learned to solve some tasks beyond recognition and mainly considering some low-level vision tasks. And we will focus on two major topics here. One is how we can use deep learning to find correspondence across images and find out 3D structures of the scene. And the subtopics including optical flow, stereo, and depth estimation. And we will also talk about how we can do use pixel level information to do image enhancement. Basically use fully convolutional network to enhance our images and transfer styles of image from one to the other. And similarly, we will also use the same technique to do supervised solution. Let's first talk about optical flow. So we discussed optical flow a while ago. The task of optical flow is we are given a pair of image, and then we define which one is source and which one is the target. Then for every pixel on one image, we are supposed to find its correspondence on the other image. And we can, in a video setup, we can find those correspondence across every pair of image and generate a visualization like we are seeing on the screen. And this is a video from a very famous Intel dataset. And as you can see, this is a simulation data. To be specific, we are given a pair of images, and then for each pixel on the first image, we are supposed to find the 2D vector u and v, so that we can move this pixel to the same point on the second image. And this gives us two ideas for the algorithms. The first type of algorithm usually look for the same point within a certain region until you can find a point with a very high similarity. The other type of point directly try to predict the 2D vectors u and v. And in the previous lecture, we talked about the famous Horn and Schrank algorithm. So we formulated the optical flow problem as a continuous function, and then we have two parts in this whole energy function. The first part is the smoothness term. The goal of the smoothness term is to have the constraint to solve the ill-posed problem, and the constraint is locally the two adjacent pixels should have similar displacement. And the other constraint is the similarity. It basically says that if the constraint vector is correct, then we should find the pixel with the same intensity. And then we introduce methods that can solve this energy function with a variational method. However, the variational method can only find some local minimum based on your current guess optical flow, or sometimes your initialization is just assuming that the flow is 0. And there, for the same energy function, along the past 30 or 40 years, people have also proposed other type of algorithms to minimize the energy, so that we can find the good optical flow to enforce both smoothness and similarity. But overall, what we find is this equation is very hard to optimize. It's especially very hard to find a global minimum for this equation. So we have several very effective shallow solutions that people have been using before deep learning. And it's basically the solutions are basically divided into two steps. The first step is the patch matching stage. It's basically give the pixel level information to tell us that given any pair of the pixel, how similar those the pixels are. And the similarity is measured by taking a patch from the neighborhood of the pixel and take the RGB values of those pixels and then use normalized cross correlation. It's basically to calculate the linear correlation between the RGB values of those two patches as a similarity measurement. And then when we have those basic similarity information between pairs of pixels, we can use global optimization to optimize the smoothness and the pixel similarity. And we try, just like what we did with the Horn and Shrunk algorithm, we optimize both the pixel matching and the local smoothness. And on the other hand, besides the variational method, people have also tried a wide range of other methods in order to optimize the energy. And those include local minimum search, and variational method is one of them. And also we have a global search guided by nearest neighbor. Basically, given a pixel from the one image, we look in a very big window of or very big area in the other image to see that what will be the correct matching for that pixel, and use that to guide our optimization of the energy function. And we can also formulate this problem as a Markov random field and use a promised global and use some approximate methods to find the global solutions. Here is the visual illustration for this process. Given a pair of images, we first use patches to describe the pixels. And basically, we are using the RGB values of the neighborhood of a pixel to describe this pixel. And you may ask that can we use some other descriptors we discussed in the previous lectures for this purpose? And the answer is actually yes. And people have tried to use SIFT to do flow estimation across images that are very different. And for our purpose, in the traditional framework, previous research find that just use RGB values actually work very well in the tradition in those methods. And then we can use normalized cross correlation to find the similarity between each pair of patches. And of course, those are sometimes we do not calculate similarity across all the patches. And then with those pixel similarity information, and together with smoothness regularization, we want to solve this optimization problem so that we can both have similar pixels for the upper flow, and at the same time the displacement for the neighboring pixels are similar. At the same time, we also talk about some challenges for this traditional method. First of all, the patch pixels usually have limited descriptive power, and the matching scores are very noisy, even if we switch to some other descriptors. Because the descriptor we usually introduce are to describe some salient points like corners or the center of a blob region. And if we use the descriptor for every pixel, they always give us some very noisy similar scores just because there are so many candidates. And on the other hand, the global optimization methods is usually very slow. So the people have, like previous research, have designed more powerful optimization methods for our energy function, and we are getting better and better results. But at the same time, the computation also become a problem. It's usually take minutes per image pair to get the state of results on CPU. And the third point is the smoothness square can be misleading. So we all know that if we are looking at a pair of pixels across the object boundary, then they are not supposed to move in the same direction. And also, when the objects we are dealing with are all 3D, so the adjacent pixel usually have a different displacement. And this means that even if we can find the exact solution that can get global minimum for our energy function, the displacement or the optical flow estimation can still be far from perfect. At the same time, the deep learning solutions we discussed last time for the recognition task seem to give us some ideas how to solve those challenges. First of all, fully convolutional network give us a very good pixel representation. As we have shown in semantic segmentation, we are able to design a network that can combine the pixel level details with high level semantic information, so that we can both have spatial information and semantic information in those pixel level representation. And also, the 2D context information is automatically considered in the output of the context in the convolutional networks, just because we are considering very deep network, and those networks have very large receptive fields. Just as a reminder, the receptive field means that for each output pixel, how many input pixels can change it. And for the networks we are considering, like ResNet 50 or ResNet 101, the receptive field is ranging from several hundred pixels to even more than 1,000 pixels. And another point is some global optimization, like Markov random field or conditional random field, can be approximated by convnets. Let me give you 10 seconds to recall where we actually see that. So we actually see how to approximate CRF for the segmentation task, and we can use a neural network to approximate the conditional random field so that we can get sharper boundaries for the segmentation results. And so far this is all good, so we can use the network we designed for pixel level prediction to describe and optimize the optical flow task. However, there is still a missing point: how we can add temporal information in our model so that it can consider association across two frames. To get started, you may say that why don't we just feed two images into the network instead of one, and use the optical flow signal as a supervision of the network. This actually can work, and this is exactly studied in the paper called FlowNet. So the initial idea here is the network can take multiple channels. Usually our images have 3 channels RGB, and convolution doesn't care how many input channels you can have, and we can just use we can even use 6 channels as the input for the convolution networks, and it is all the same. And also at the output, we can at each pixel we will have a displacement vector as a prediction signal, so that we have supervision and we have input. Now we can just use stochastic gradient descent to optimize the network so that at the testing time it can give us the desirable output. However, we find that some additional components for the network can actually improve the method dramatically. And this, ironically, is actually very similar to the ideas we discussed in the traditional methods. So the process is like this. First, we can have a separate network to extract the features from the model, just like what we did for patch level to extract patch from each pixel. And because here we can use a GPU and convolutional network, we can extract every pixel very efficiently. and at the same time, we can calculate the correlation between each pair of pixels. Of course, in certain range, we cannot afford to calculate the feature correlation across every pair of pixel. We only need estimate like how big our maximum displacement is, and then only do a correlation within that range. And this does give us some some correlation information between the features on two images, and that's very similar to what we did on using normalized cross correlation to measure similarity between two patches. And we can use our network to keep keep scrambling the correlation information together with the picture level information. Here, the solution is to concatenate them together, and then pass them into another deeper network. And here we can use upsampling or deconvolution to restore the resolution of the original input image, just like what we did for semantic segmentation. And of course, we can use certain pathways to pass additional information to the upsampling, so that we can have some more spatial information to get for the upsampling part, and then we can use this information to get the to learn how to predict the optical flow at the end. And as you may remember, when we talk about semantic segmentation, we say that we have to first train the model weights on image classification task, and then using those weights to initialize the very deep models for our segmentation task. And the reason for that is it will be very hard to bootstrap the model or the weights using the limited semantic segmentation data. Usually, we can easily find millions or tens or even hundreds of millions of images for the classification task, just because it's very easy to tag an image, and it's very hard to tag the pixels within each image. Consider an HD image; there are like millions of pixels within on each image, and even though that we are doing polygon annotation on the images, it's still a very challenging task and time-consuming to label the segmentation mask. So it's actually the same when we study optical flow, we actually see the same problem. And so as you can see in the previous slide, the model we are designing are not rooted on the image classification network for the computation efficiency. So how can we train such a model? And even the idea here is to use more simulation data. And even though that we have some traditional simulation benchmark like Sintel, but we find that the amount of data in the existing simulation data at that time was still not enough. And in this work called FlowNet, so in the exact same work that studied the network structure, they also proposed a training dataset called flying chairs. And the flying chair is yet another simulation dataset. It's actually very simple, and sometimes you can even call it naive. So it's trying to have both photorealism in the synthetic data, at the same time to have ground truth optical flow to bootstrap the models. And their solution is they first get a set of 2D images, like the natural images, and then using some CAD model of chairs, and do some rendering on the chairs. So the chairs, as you can see on the pictures, the chairs themselves look like rendered and look fake, and they just randomly throw the chairs into the image, and therefore the dataset is called flying chairs. And the good thing about this dataset is it's very easy to generate a large amount of data in this method, and because we have the exact 3D model for the chairs and their location in 3D, we can get the very accurate optical flow ground truth. Then after we use we get this flying chart dataset, we can use it to first pre-train or bootstrap the FlowNet model. Here is a demo of the results. So as you can see, the model is ambitiously run on a laptop, and we can still achieve a very high speed. And unlike the traditional methods, which may run like many seconds on the low-res images. And here is showing that if we use correlation in the network, it actually can be better than the naively structured FlowNet. And this FlowNet can also get a flow for some very small structures, like the scissors. The results of FlowNet are very encouraging. They are very efficient. They can be run almost real time on even commodity hardware, and at the same time, they can achieve decent accuracy. However, there is still a performance gap between the deep learning methods and traditional methods on the popular benchmarks. So to close the gap or to even get better methods, we can keep borrowing ideas from the traditional method. And here in this work called PWCnet, and we can see that the method mimic exactly the traditional pyramid scheme. Oh, here I call it pyramid scheme for the for calculating convolution, for calculating optical flow. So in the traditional method, we usually have a image pyramid with different resolution. The goal here is it's usually very easy to find the correspondence on the low resolution image because the range of optical flow search is very small. And then we can use those optical flow at a coarse level or at low resolution image to bootstrap and guide the optical flow at the next level, so that we do not need to perform perform a search of optimization across very large area. And this guidance is achieved by using warping. Basically, we can have optical flow on the coarse level, and then we can upsample the flow just by multiplying the vector by 2 and interpolate the optical flow for the high resolution flow map, and then use that upsampled flow to warp the second image. And then we basically say that the displacement between the first image and the warp second image actually becomes smaller because the upsampled flow map has already offset some of the flow displacement. And then we can calculate the flow from this warped image and the first image again, basically using our energy minimization to find a new flow. And basically we are finding residual of the flow between the warped image and the target image. And we can do this again and again until we get the desired resolution. So this has been very successful on the traditional methods. And then we can use the same idea on the convolution network as well. And because on convolution network, instead of a pyramid of images with different resolutions, we can use a pyramid of feature maps, which are supposed to be more descriptive for the images. And then for each level, we can calculate the optical flow, and starting from the coarse level, calculating the flow vectors, flow values, and then use it to warp the feature maps and warp the feature map on the next level, And then on the next level, calculate the feature display, calculate the flow displacements from the first pyramid to the warped features, very similar to what we did in the traditional methods. And then we can add this warping layer. The task is to given an input flow vector, warp the feature vector, warp the feature map, and then calculate the cost volume. The cost volume layer is basically the cross correlation, and then we get this cross correlation information. Use it to calculate the optical flow, which serve as a convolutional version of energy minimization to find the refined flow map, and then use this refined flow map to guide the flow estimation at a next level or at a finer level with higher resolution. We should introduce a very important technique here to achieve warping. So in the network forward path, warping is very intuitive. We are giving a set of displacement vectors, and then we can directly just use image sampling or traditional warping to find the output feature map in the forward path. However, in convolutional network, we need to make sure that every operation is differentiable, and not only we care about the layer output, but also the gradients of that layer operation. So to resolve that problem, we are taking ideas from this work called spatial transformer, and as we shall see, this technique has been used again and again in a lot of tasks. So this diagram shows a case that this spatial transformer try to consider. That is given a input feature map U and output feature map V. So we have a localization network trying to tell us that for each pixel in V, where we are for each feature location in V, how we can find its features from U, or how we should sample the features from U. So for example, U and V can be identical, and then for each feature location on V, it can directly find the feature on U on the corresponding location. And it can be much more complicated. For example, we can rotate the feature vector of U, and then this whole parameter will generate the rotation and the rotation displacement. And with those displacement, we can use this sampler to find the corresponding pixels from U. And this sampling procedure, it can be expressed like this in general. So this is the output pixel, and it's we are omit the xi and the yi, and we have U, which is the cost volume with w with width and height. Then for each location, we are considering a kernel function here. Like basically, for each output pixel, we are considering that everything on the input pixel and the input location with that location on the input feature map. And here we have some parameters for the kernel dictating that how we should sample from that input location. So here is a simple example of how we can use this sampling function. And this equation expresses how we can do nearest neighbor sampling. And so as you see in the previous slide, we have the output V and the input U, and we are considering every pixel for each output location of V, we are considering every pixel on the input. And here the kernel is a delta function. And as you can recall from your basic calculus class, so the delta function is only 1 when its input is 0. And as you can see here, so we are only considering the locations around the sampling location xi and yi. So even though that we are summing across the whole feature map, but only the location that is corresponding to the rounding of xi and yi is meaningful for this equation. And in implementation, we can also speed up the computation by ignoring the other locations or the locations that will be far away from xi and yi. Here, xi and yi can be any number, and we are using this part to round it to an integer. So because we can know this kernel function beforehand when we construct this sampling, in reality, when we do this operation or we implement the operation on GPU, we can even manually reduce the computation complexity so that in real computation it doesn't consider the summing for the whole feature map. But with this expression, it is easier to consider the gradient and deducted from the general form. So here is an example. Our localization network may consider the parameters of rotation and find the center of the digit. Then our sampler will generate the points for this rotation operation, and then propagate those points to the output pixel so that the digit can be rectified based on the estimated rotation. The other part of PWCnet is easy to construct with what we have already learned. For example, to do a feature pyramid, we can just extract features at different levels of the network, just like how we do upsampling FCN, and with correlation is essentially a dot product between two vectors, and very easy to calculate the gradient of that operation. But overall, with this pyramid structure and the coarse to fine calculation of optical flow, we can get much better efficiency and at the same time much better performance on standard dataset. Basically, at this level of performance, we can claim that we can use deep learning methods to replace the traditional methods for the optical flow task. Although the deep learning-based optical flow methods are achieving impressive efficiency and accuracy, but there is still one drawback. In the current networks, we are directly regress the displacement or the optical flow values. In this process, we are not considering the strength or uncertainty of that optical flow displacement, and we know that is in some region, like especially in a occlusion region, it will be very hard to get the correct optical flow value, or sometimes it's even impossible because of occlusion. But the regression value will always tell us a value without telling us that how certain the network can be, and that can lead to some problem in terms of integrating the optical flow results in the downstream task. Basically, given the optical flow values, we do not know that which value we can trust and which value we shall dismiss. And this is considered in a follow-up work. And in this work, the authors consider the technique called hierarchical discrete distribution decomposition. So the idea here is, instead of considering the displacement in the prediction, we convert the displacement estimation to a probability distribution estimation. The idea here, to be specific, the idea here is at a coarse level, we can first discretize this image into several bins, and say if we want to calculate the optical flow for this particular pixel, we will first get a probability distribution of where the flow can be in that neighborhood. Of course, this is the first image, this is the second image. And then on the second image, you can see that we have a set of grids, and in this neighborhood, say 3 by 3 neighborhood, we can find a probability distribution where the correct matching can be, which bin that correct matching matched pixel is. And this bin can be very coarse as long as we can locate which bin it is. And then we can further construct a finer grid across that predicted bin, and then estimate the probability of which bin the correct matching can be. And we can do this iteratively until we get the correct correspondence. As you can see here, even though that we are considering probability distribution, but this process is very similar to the warping. We are basically saying that given the probability distribution at each level, we use it to guide the searching in the next level. And we can actually implement this based on warping. However, there's another barrier for us to achieve that. That is how we can convert the probability distribution to the input for warping. And we actually can define two operations here. One is D to V, distribution to vector, and V to D, vector to distribution. You can see that here in this neighborhood, we have a probability distribution. Say on this 9 pixels, we say that 40% of chance the correct match is in this area, is in this bin, and 20% chance in this bin, 20 in this bin, and 20 in this bin. And we can find the neighborhood here, 2 by 2 window with the highest density, and then within that density, we can find the center of the mass and convert that into a vector. And when we want to convert the vector back to a distribution, it's the same. So here we consider the grid of this space and see that which 2 by 2 neighborhood this actual vector is in, and then we can spread this point into as a probability into the neighborhood. For example, say we can say that how basically it's the same procedure from D to V, but we are considering that how close this vector is to each target grid, and then we use that normalized distance as the probability in each grid. Please note that the support of this probability is the range of the size of the grid, and then we are assigning probability value into each cell in this grid. The results are very encouraging. So the left two columns are the images we put here as a part of the illustration to show you that the resolution we are observing at each level. And then this is the downsampling of the ground truth at each level. We actually also use those ground truths at each level as a supplementary supervision. And those are the prediction results. And you can see here for each level we can also predict the error map to see that where the object can go wrong, and what the distribution estimation can provide us in addition is the confidence map. It tells us that each location how uncertain we are or how confident we are. So you can see here at the finer level, the white means confident and the black means unconfident. And the uncertain areas indicate clearly that where the motion boundary can be, and those has a very high correlation with the occlusion and also where the network may make mistakes. Here are some more results of this type of multi-scale methods for optical flow estimation. You can see that our model can estimate the multiple parts of the image quite well, as shown as the blue area. But for the small structure and the occlusion boundary, the error map is usually higher. So overall, deep learning methods for optical flow has beat the traditional methods in both accuracy and efficiency. And nowadays, if you want to do optical flow, very likely you will just grab a state-of-art methods on on the optical flow benchmark, and there must be a deep learning based methods. And also, if you want to do real-time accurate optical flow estimation, it's also possible. And however, at the same time, as we also observe that the dominance of deep learning method doesn't mean that our research on traditional methods is not useful. A lot of those ideas has been carried out into the new era, so that we can quickly find new methods and new structures of convolutional networks based on those traditional ideas. Now let's talk about a very related question, stereo vision. So the stereo vision arises from a pair of synchronized frame that observing the same word at the exact same time, but from different viewpoint. And our goal here is to find the displacement of the object across two images. And with those displacement information, we can reconstruct the 3D structure of the world just based on simple geometry. And it's actually very similar to optical flow in the sense that we want to find the correspondence from of the pixels on the first image to the second image. However, instead of being a 2D search, stereo vision is actually a 1D matching problem. And that's because we only need to search across the IP power line. We do not need to consider the other areas on the image. And even so smooth prior is still useful. And because we have a smaller search space, we can still use patch matching and global optimization 2D on the 2D space, but the search space can become smaller. And so the relation is still 2D, means that we are still saying that for each pixel, it can have similar depths with its neighbors. And because of the similarity between stereo vision and optical flow, the deep learning solutions are also very similar for to those for optical flow. And basically, we can just use optical flow methods for stereo vision, and the only difference is we only need to do 1D correlation and predict the one vector for each pixel, one value for each pixel, instead of 2D correlation and 2 vectors for optical flow. Due to this similarity, we can directly use AZ3, the method we introduced just now, on the stereo problem. So here is a standard dataset on stereo, and as you can see, it's actually also a simulation data. And here is the ground truth, and this is our prediction results. So it's very close to the ground truth, as if we see that visually. And this is the arrow map. As you can see, the arrow are mainly on the boundary regions. And here is the confidence, which a good indicator where the errors can occur. In 3D vision, we learned that if we have the correspondence of the stereo image pair, then we can have very good depth estimation for the whole 3D scene. And what if we only have one image? Can we still estimate the depth for the scene? This is clearly an ill-posed problem, and this is very challenging for the traditional methods. But with the powerful pattern recognition methods brought by convolutional networks, we may be able to solve this. We may be able to get much better results on this ill-posed problem. And first, this is a typical dataset we consider in case of single image depth estimation. So we have a calibrated pair of the RGB image and the depth, and the depth is usually LiDAR scan, which is very accurate measurement of the 3D distance. And our goal is to predict depth from 2D image. And as you can imagine, this type of supervision is very uh, general on its current self-driving platforms. Basically, we can easily project the lidar scanning points on the 2D images, and the lidars are equipped on most of the self-driving car platforms. And if we can estimate the image depth from single image, then we can directly use a large amount of data to supervise the training, and maybe we can achieve very good performance and eventually get rid of lidar when we deploy those platforms. The initial work on this direction consider how we can do this, how we can do a multi-scale estimation. So as we have seen again and again from segmentation and optical flow, this type of multi-scale or coarse-to-fine estimation is very popular for pixel level estimation. And because the work is very early, so at that time they were not fully aware of the other type of backbones and convolutional networks they can use to represent pixel level information. So they actually design their own network like this, and they, as you can see here, the structure is very similar. So they first do multiple convolution each block, and then gradually downsample the resolution to get a coarse level estimation, and then feed this coarse level estimation into another network with higher resolution, basically to provide the spatial details, and combine it with the coarse level information to get a refined estimation. As you may remember, this is very similar to the fully convolutional network we introduced for segmentation. And for this fully convolutional network, in order to get a higher resolution from the low resolution but deep convolutional network, we can gradually combine the high level layer feature map with lower level layer outputs, so that we can get both spatial resolution and semantic information, and we can do the iteratively to keep increasing the sampling. And we also discuss the drawback of this scheme and discuss a lot of some other alternatives. So it's apparently this type of idea is also useful for depth estimation. And nowadays, if you want to do this similar type depth estimation, you may turn to the existing fully convolutional network that has been fully proved on semantic segmentation task. But there are also other things we need to consider for depth estimation. The first is data augmentation. Some of them are commonly used in the other task as well. For example, for scale, we augment the data by different level of different sizes, like basically scale up the image, and rotate the image a little bit so that we can also be rotation invariant in training. And of course, translation and jitter the color, and also flip the image horizontally. But there another special consideration, which is the output encoding. In semantic segmentation, the output encoding is very easy. It's basically the softmax, or the probability for each category, and then we penalize that probability or calculate loss of that based on that probability based on log likelihood. For depth estimation is more complicated because depth is a continuous value, and in addition, depth uncertainty also increase with the depth, which means that if the depth is very far away, the uncertainty or the variance is much bigger than the depth nearby. And this is also the case for the stereo vision. So when this is especially true for the single image estimation. even if we have some geometric cues we can use to estimate the depth, but the further the object is, the higher uncertainty we have. And its direct consequence is if the uncertainty is very big, then the error will definitely be big. Basically, it says that the expected minimum error should be the uncertainty, or should be the variance of that depth. And therefore, instead of encode the depth directly and calculate the L1 loss between the ground truth depth and predict the depth, we usually use some alternative depth encoding. For example, we take a log of the depth, and then for the far away, when the depth become bigger, is the log scale. In the log scale, the depth the encoding will increase much slower, which will encourage the network to learn good depth for nearby and not be perturbed by the noise far away. And we can also use inverse depth to achieve similar effect. And also we can also do a depth range quantization, basically convert this regression problem into a classification, and which is more immune to the noise at a different level if we quantize the depth properly. And here are some results of these proposed methods. So those are some indoor images. They are captured by a Kinect, so we can have the ground truth obtained by the depth sensor on Kinect. And then this is the coarse level prediction. As you can see, it gets a rough structure of the scene. It just looks very blurred. And after we refine the structure, we can see a lot of geometrical details on the prediction, like the cubic structure for the bed, and the depth for the other parts of the room. Even though the depth sensor has been very popular, and with the availability of self-driving cars, we get more and more data with calibrated LiDAR and image pairs. But the majority of the videos, for example, the videos we take by our cell phones, are still monocular, and we do not have direct depth information to learn how we can estimate the depth on single images. And in this case, we can actually turn to the temporal information and turn to the video structure for depth supervision. This is very similar to SLAM. Basically, from a monocular video, we can estimate the depth for the scene and use that as a supervision for a single image depth estimation. And we can use convolutional networks to learn how we can perform single image depth estimation. So from multiple images instead of the depth sensors, and potentially that can make the depth estimation methods be applied into more situations. A basic structure of such a solution can look like this. We start with a set of unlabeled video clips without depth data, only the videos sequence, as we can capture from dashcam camera and cell phones. And then with those views, we can have two networks. One is to predict the depth of the view, and then the other is to predict the pose of the view between the two views, and then combine them together to estimate the 3D structure. And the supervision signal we can obtain here is very similar to the loss we trying to optimize for the structural motion. That is, we want to minimize the photo consistency based on the depth estimation. Say we have a target frame, IT, P, and we have a source frame. We want to warp the source frame based on the depth estimation, so that the target frame and the warp frame look exactly the same, and that will be our loss. And here in this expression, we are using L1 loss. Just as a reminder, L1 loss is usually considered more robust than L2 loss, since L2 loss will put more emphasis on bigger error values. And to obtain the warped target image, we can do a transformation like this. So we start with the pixel location on PS. So we hope that we can find the PS that will correspond to a pixel on PT, so that we can warp. So that given we can warp from the source image to the target image, or in the other way, for each pixel location on the target image, we can find the pixel location on the source image. And then the transformation will look like this. So we first use the camera intrinsic to represent the point into a canonical 3D space, and then use the estimated depth to find the exact 3D location of this point in 3D in the targeting camera frame, and then use the output of the postnet to transform the 3D point from the targeting camera frame to the source frame coordinate. And after we have after we transform the point into the target to the source image frame coordinate frame, then we can use the intrinsic to project into 2D and find its location on the source image. Again, let's look at this picture to understand this process. We have a sequence of images, and then for each image, we will pass the like for the target view, we will pass it to a depth, and then we will estimate the depth at each pixel, and then we will represent this depth pixels based on the depth and the estimated pose to the nearby views, and measure the photo consistency and use it as a loss to train the network. Here we want to train both the postnet and the post CNN and depth CNN, so that we can optimize them jointly and get the good photo consistency. And at testing time, we can directly use the depth or even the post CNN to estimate the information we need. And as you can imagine how it should be estimated depth, use a fully convolutional network structure or use a UNet structure to get a deep representation, and then do upsampling by integrating the deep representation with the lower level layers, which has more spatial information. And it is the same for the post estimation. But for the post estimation, we only need to get one set of parameters, basically like image classification. Only get a image level prediction to estimate an R and T from the pose. And in this particular work, they also add a explainability network. This part will estimate that will tell us that which part is moving objects, which part of the image cannot be explained by this pose or by this transformation. It was mentioning here that the image warping also use spatial transformer in order to warp the image and make it differentiable. And here are the results we can obtain from this method. As you can see here, even though that we do not have the full 3D supervision and in the training time, but the depth estimation from this method still looks reasonably well. And the good part about this method is it doesn't require any supervision, so we can run it on any video available and get the depth, and then use it to predict predict depth on the other image in the same scenario.